Yeah, futurism. Scientists say the laws of physics may be changing. No, or maybe it's the other way around. The cosmos is stranger than we know. You know the old saying, the only thing constant is change? But we Wager most people don't think that line applies to the actual rules of the universe itself. As it turns out, though, researchers at Microsoft, along with scientists at Brown University, even one expert who consulted for Disney's Wrinkle in Time, think the laws of physics might actually be slowly changing, complicating our quest to understand the cosmos. Yeah, the laws of physics don't change, just your perception, your understanding of it. Popular Mechanics published a lengthy explainer this week about a paper titled The Autodidactic Universe, and published earlier this year, in which the team argued for the precise mind-bending hypothesis. An autodidact, of course, is someone who learns without a mentor or teacher, and these researchers say the universe itself may be one. We ask whether there might be a mechanism woven into the fabric of the natural world by means of which the universe could learn its laws. The authors wrote in the paper, which has not been yet peer-reviewed. Yeah, it might be quite a waste of time. Over time, the theory goes the universe has sought stability. PopMech draws parallels to animal evolution too. There are no trilobites or dinosaurs anymore, but cats and dogs have survived because they adapted to the environment around them, and the cosmos may have done the same. In an early version of the universe, for example, Newton's laws of gravity, that all matter in the universe attracts other matter with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between the centers, might not have been true yet. Because gravitational force is an electrical force, it's about the charge. Over time, that system will teach itself and some fundamental laws will arise, and that's really what they are talking about. Janna Levin, a professor of physics and astronomy at Barnard College of Columbia University, who wasn't involved in the research, told PopMech. If the universe can compute with a given set of algorithms, then maybe it can do the same kind of thing we see in artificial intelligence, where we have self-running systems that teach themselves new rules. And by rules in cosmology, we mean laws of physics. The paper's authors also acknowledged their own skepticism and wrote their conclusions with caution, warning that their work is only a baby step in the formation of a new theory and requires additional research. Of course, this is just the first step, the authors write. There are varied potential spin-offs of our approach. It's mind-bending to imagine that laws of physics might learn and adapt over time. But it reminds us that the universe is stranger than we'll ever know. Yeah. So now let's go to some other article which actually makes sense, because this was total crap here. Waste of time. I just wanted to show you this. Now we are at physics.org. We are still in Newtonian science. Tuning a magnetic fluid with an electrical field creates controllable dissipative patterns. Oh, really? Researchers at Aalto University have shown that a nanoparticle suspension can serve as a simple model for studying the formation of patterns and structure in more complicated non-equilibrium systems, such as living cells. The new system will not only be a valuable tool for studying patterning processes, but also has a wide range of potential technological applications. The mixture consists of an oily liquid carrying nanoparticles of iron oxide, which become magnetized in a magnetic field. Under the right conditions, applying a voltage across this ferrofluid causes the nanoparticles to migrate, forming a concentrations gradient in the mixture. For this to work, the ferrofluid has to also include docusate, a waxy chemical that can carry a charge through the fluid. The researchers discovered that the presence of docusate and a voltage across the ferrofluid resulted in separation of electric charges, with the iron oxide nanoparticles becoming negatively charged. We didn't expect that at all, says Carlo Rigoni, a postdoctoral researcher at Aalto. We still don't know why it happens. In fact, we don't even know whether the change already gets split when the docusate is added or if it happens as soon as the voltage is turned on. To reflect the noble sensitivity of the electric fields, the researchers call the fluid an electroferrofluid instead of merely a ferrofluid. This electrical responsiveness causes the nanoparticles to migrate, and the resulting differences in the nanoparticle concentrations change the magnetic responsiveness of the electrofluid. As a result, applying a magnetic field across an electrofluid changes the distribution of the nanoparticles with a precise pattern depending on the strength and orientation of the magnetic field. In other words, the nanoparticle distribution is unstable, shifting from one state to another driven by a small change in the external magnetic field. The combination of voltage and docusate transformed the fluid from an equilibrium system into a non-equilibrium system that requires constant energy input to maintain its state, a dissipative system. Our planet is a dissipative system. It just and only works because there is an constant energy input from the outside, which is also creating the magnetic field, which is shielding us from stuff which is like coming from outside, like this, all kinds of solar wind things and cosmic rays and all these kinds. It's the magnetic field which is shielding us quite much from that, and also keeps the clouds quite close to the surface and our atmosphere in place, that there's life possible here. But anyway, these unexpected dynamics make electroferrofluids particularly interesting both scientifically and in terms of potential applications. Ferrofluids have drawn the attention of scientists, engineers, and artists since their discovery in the 1960s. Now, we have found a truly facile approach to control the magnetic properties on the fly just by applying a small voltage to drive the fluid out of the thermodynamic equilibrium. This allows a complete new level of control of the fluid properties for technological applications, complexity in the pattern formations, and perhaps even new artistic approaches, says Jaakko Timonen, a professor of experimental condensed matter physics at Aalto, who supervised the research. Dissipative driving is a general mechanism creating the patterns and structures all around us. DNA, clouds, mountains. Not all of the mountains, but most of them. Life is an example. Organisms have to continually dissipate energy to their ordered state. And that's also true for the vast majority of patterns and structures in the ecosystem. If you meet someone who is low, he's not well, like he's sad or whatever, you can say he's on low frequency. So he has a low charge. If you pump him up with something positive, give him some positive input, he will be running on a higher frequency, so his overall charge is higher. Like your thoughts and the clouds in the heavens, they have one thing in common. They are held together by electricity. So if your charge is low, your thoughts don't stick together. They run around and you get depressed because you can't think clear. You get distracted and anxious and whatever. And if your charge gets higher, you will hit the truth, the real truth, more often. And you're just running better because you have a higher charge, and through that, a higher frequency. You look better. Everyone can see. Everyone sees when you're sad. Everyone can see when you're angry. Everyone can see when you're happy. It's obvious. It's visible. Rigoni explains that this discovery provides a valuable model system for researchers trying to understand dissipative systems and the pattern information they underpin, whether in the form of living organisms or complex non-living systems, such as mountain ranges. Most dissipative systems are very complex, for example. It is very hard to reduce living systems to a set of single parameters, which could explain the emergence of certain structures. The voltage-driven ferrofluid can be used to study transition. The voltage-driven ferrofluid can be used to study the transition into a dissipative system and understand how external influences such as magnetic field interact with the system to generate or modify structures. This could give us hints about how dissipative structures in more complex contexts are created. I claim that our blood is this kind of ferrofluid. What was it again? They gave it a new name. Ferrofluids. But they get not forgetting. Anyway, our blood is a ferrofluid too. This also indicates, since it goes through our brain, it might have more impact than many scientists think. Like if you're on low charge and your blood is running low and then it goes through your brain, you will be on low charge. But it's also about the conscious level on what you are, like realizing that you are now on low level and you really have to work on that, not feeding the bad wolves. Make a conscious decision about what's going on with you. Now I'm really angry. Actually, I don't want to be angry. So there would be reasons to be angry. There's one single reason why you got angry. That's why you're angry. But if you take one step back and look at a little bit the bigger picture, you will probably figure out that, yeah, actually, that's just a small thing, and I'm really angry about that. And so much energy goes through to that, or into the state of being angry. And this energy could be also used for something else, which would be probably more wise to use it for something constructive. So it's also about your own perception of your reality. Like, if you all of a sudden are aware of your state of mind, why you are in this state of mind, what were the happenings, what led you to be in this state of mind right now, it's really easy to find a million things to get angry, sad, disappointed, anxious about. It's really easy. But it's so much harder to find these things which have the same magnitude of influence on the positive side. It's up to you to make the decision to, how to put it, naturally, like bad things, they matter. They take you down because they take you down because they are so heavy to bear. Like the whole weight of the world is on your shoulders. Yeah, okay. So, if there's so much weight in the bad, there should be so much pull up in the good too. But it's overseen too much in nowadays culture because you have to work to be happy. If you don't work, you will never be happy. If you don't achieve anything in nowadays, or how to put it, in nowadays modern society, if you don't achieve anything which is somehow visible, new car, new house, and whatever stuff, what you can show, it's worth nothing. You know? It doesn't matter. Even though it's like matter, like a car is really heavy. But it doesn't matter in the way that it could be transformed in energy, and I'm talking about positive energy. Like all those people who spend all their lives playing some video games and figure out like how this kind of world there works, how to win that war and this mystery, and figure out how it's working and what's the secret of that. Why are they wasting their time in a video game world which is fictional from the beginning to the end? There was like much more interesting things happening in the real world. And I'm not talking about the real world which is brought to you by mainstream media, about the real world. Because there are too many scientists out there. They just don't know that they don't know. But still, they are fighting so hard to defend their paradigm they are in, even though they don't even know that they are in a paradigm. They don't know that they have to obey the rules of the paradigm they're in. They just don't, they can't see out of the box because their box is obviously really sturdy. And this is somehow like, if you compare those two articles between, and like those recent I made about like interstellar mysterious structure and all these kind of things, how is it possible that those people don't see those things, that they are like basically they have the same origin? It's somehow unbelievable. Or made on purpose in order to confuse those who try to see behind the scenes of modern science. I don't know. I'll leave it here. Thanks. Bye.